In this video, we're going to continue with the electron transport chain. And in the last video, we ended with cytochrome C getting electrons from coenzyme Q in complex 3. Now, cytochrome C is different than complex Q in that it is soluble in the intermembrane space, while coenzyme Q was more or less a lipid soluble in the membrane. Now, cytochrome C will take electrons from complex 3 and bring them to complex 4. And it's doing this in the parts of the enzymes that project above the surface of the inner mitochondria membrane. This protein has very highly conserved lyse residue and a ring around the exposed edge of its heme group that's buried inside of the protein. This binding site, it's complementary negatively charged groups on cytochrome C1 and C oxidase. And these groups allow it to be aligned so it is in perfect arrangement to get electron transfers. Now let's move on to complex 4, our last numbered complex in this process before we get to ATP synthase. Now, complex 4 will get 1 electron from cytochrome C in 4 consecutive cytochrome C molecules. So 4 cytochrome C molecules will come to complex 4, and they will reduce 1 oxygen molecule to make 2 different water molecules. So the overall reaction is 4 cytochrome Cs plus 4 protons plus oxygen will give you 4 cytochrome C now oxidized into water molecules. Another massive complex here, 410 kilodalton homodimer. Each protomer or dimer, monomer of the dimer, is composed of 13 subunits. 10 of these subunits are transmembrane proteins. And the core of this complex are very large hydrophobic subunits. Now let's look at the redox centers of complex 4, and we have 4 different redox centers here. We have cytochrome A, cytochrome A3, copper atoms, which we call copper B, and a pair of copper atoms that we call copper A. So here's copper A, here's our different hemes, here's copper B. So copper A is bound by sulfur from cysteines. This is very similar to our iron sulfur complexes we saw in our other complexes. Here we have a linear transfer of electrons from cytochrome C to copper A to heme A3 to copper B. And here's our oxygen molecule that's receiving all of these electrons. And the way these electrons are moving is through hydrogen bonds in our amino acid side chains. Now let's look at the currently proposed reaction for how we have electrons moving through complex 4. So remember, we're taking O2 and reducing it to water, and this is at our A3 copper B binuclear complex that we saw in the previous photo. Now, to do this, we basically need the input of our 4 electrons all at the same time. Now, our iron-copper complex can only give us 3 electrons, so we have a side chain tyrosine, which is giving us our 4th electron by becoming a tyrosyl radical, or a radical tyrosine. So we start here on the image here, and we're going to talk about step 1 and step 2. So we begin in our already oxidized state where our complex, our iron-copper complex, has an OH minus attached to it. We have our tyrosine in the phenolate state where we have our O negative, so there's no hydrogen on tyrosine. And here's our copper complex. We have water attached to it already. And what's happening is that we're going to have 2 consecutive 1 electron transfers. So even though they're steps 1 and 2, they're happening at the same time. So cytochrome C is coming in and on both steps 1 and 2, we're given electrons from cytochrome C, and we're giving it to our copper A and our cytochrome A until we're getting to our complex as pictured. So we have an electron come in. We also have a hydrogen coming in from our matrix. Water is released from our copper. We're at copper 1. And now our iron is still negatively charged with our OH, so our iron hasn't changed in step 1. But our tyrosine now is back to OH tyrosine, and the copper has lost the water. Then in step 2, we have another cytochrome C coming in at the very same time as step 1, remember. We have a protein from the matrix, or a proton from the matrix again. This proton is going to connect to our OH on iron 3. We release another molecule of water, and now we're at iron 2. And tyrosine is in our, I have P state here, but that should be our R state. So after just 2 steps, we have released our 2 molecules of water, but now we have to regenerate our enzyme back to where we started. So that's what our next steps are going to do. So we have oxygen binding to our R state. So oxygen is going to come in and bind to our iron atom. Then we just have a movement of electrons between our reaction center here. So we have the hydrogen from tyrosine and one of the oxygens from iron. They're going to move and bind to our copper here. So that's what's going on here. We're going to have an electron from our tyrosine. That's going to be donated as well. And we're left with iron 4, double bonded to only one oxygen, which has an overall -2 charge. Our copper is now OH minus, and our tyrosine is our radical form. So that's what happened in step 4, all internal. Step 5, another cytochrome C is coming in. Another proton is coming in as well from the matrix. And that proton is going to, and the proton and electron are going to copper 2 to have copper 2 bound to water again. So now copper 2 is fully regenerated from where we started from. Our last step, our final step, another electron is going to be coming in. And another proton from the matrix is going to come in. And that's going to give us our iron 3 OH state. And that electron is going to come to our tyrosine. So we're back to the O state. We're no longer in the radical. And so this reaction happened more or less at the same time. And that is how we're transferring electrons from our complex 4 to our oxygen, which is appearing in step 3 here, and we're releasing water throughout this whole process. Now, we're contributing to our transmembrane proton gradient in 2 different ways. One, we have 4 protons that are coming from the matrix, and so we're binding that onto our enzyme and eventually releasing them as water, so they're no longer free hydrogen molecules, so we're depleting the matrix hydrogen concentration. We also have protons being pumped out of steps 3, 4, 5, and 6. So it's not really shown here, but during this movement, protons are being pumped from the matrix to the intermembrane space. So every time this cycle runs, we have 8 protons from the matrix plus oxygen plus 4 cytochrome C. Those are going to go to cytochrome C that are now oxidized. We're going to make 2 water molecules, and now we have pumped a total of 4 protons into the intermembrane space. And that is all for this video. I will see you in the next one.